Hey y'all, welcome to lesson 4.6, where we are going to be talking about electron dot diagrams or localized electron models. Um, Scientists use models a lot because, especially when we're talking about atoms and molecules, we can't see the individual atom, we can't see the electron, so we have to use a model to be able to talk about behavior that electron is exhibiting, like what is going on. Because we can't see it exactly, we can use a model. And the model that we're going to be talking about here is called the localized electron model, um, abbreviated LE. And there's a couple of assumptions that we have to talk about if we're going to use this model. The first assumption is that we are assuming that a molecule is made up of atoms that are held together by shared pairs of electrons. So these pairs of electrons are orbiting around both atoms. So electrons are being shared by two different atoms or more, which causes them to be in close proximity together and held together. The second assumption that we're going to make is that these electron pairs are assumed to either be close to one atom or in the space between two bonded atoms. So the electrons are either closer to one of the atoms or in the middle between the two atoms that are being bonded together. We call those electron pairs that are located on one atom, they are called lone pairs because they are off alone. And then the electrons that are in the space between two atoms are called bonded pairs. And you can see here in this picture of the model, up here we have two fluorine atoms, that's what F stands for, that are bonded together. These electrons here that are in between the two fluorines, those are the bonded pairs. And then the two here that are close to one of the atoms but not in the middle, these are the lone pairs. And all of these others are also lone pairs. Remember, we learned briefly about that octet rule that each atom wants to have 8 electrons around it in order to be stable. Well, these fluorines have 8. 2 of them are bonded pairs, and then 6 of them around each of them are lone pairs. And because these are bonded, they're shared between the two atoms. So these two count for this and this element. Because they're bonded, they're using them together. Even though we see them that way in the picture, in reality, the electrons might not necessarily be in that exact location. But this is a model, remember, and we use it to help us see what's going on and to get good information. So that's just the way we draw them, right? These electron dot diagrams are also sometimes called Lewis structures, and they only represent the only electrons that we care about are the valence electrons. And so we are seeing just the valence electrons. Those inner shell electrons are not important to what we're doing, so they're not represented. Okay. And last thing we want to say about these, on these neutral atoms, the placement of the electrons is not important. It doesn't really matter, right? What matters is that you get the right number of dots. It doesn't really matter where you put them. So let's look at nitrogen. Nitrogen, if you remember and you look at your periodic table, it has 5 valence electrons. Okay? So I can put those 5 valence electrons, as long as I put 5, it doesn't really matter. If I want to put 2 here, 1 here, and 1 here, and 1 here, that's fine. If instead I want to put 2 over here, that's fine as well. Maybe I want my second one over here. That works too. I can even put it down here. That works as well, because there's 5. The one thing that is important is that there are 5. We usually keep them, we don't put more than 2 on a side because A, we're talking about pairs, right? Lone pairs, bonded pairs. So we usually don't put more than 2 on a side. And also, when we talk about, well, let's change this really quick to neon, which has 8 valence electrons. 8 fits nicely, 2 on a side. And it's nice and even. So it doesn't really matter where you put those dots to represent the electrons, except for 2 things. 1, you get the right amount. And 2, the fact that we usually only put 2 on a side. You can see here, it doesn't show up great on my screen, but it does on your notes. Here's a few of the, around the first 17 electrons. Elements, sorry. And their electron dots, however many they have. You can see hydrogen is 1, helium has 2. And we kind of go on from there. You see the dots shown for the valence electrons. When we talk about ions, ions work a little bit differently. Remember, ions are atoms that have either extra electrons, which makes them negative, or are missing some electrons, which makes them positive. So when we draw electron dot diagrams of ions, we do a little bit different. Couple things we want to write here. So negative ions often will show the electron configuration of the next noble gas. Includes that electron, those extra electrons. Positive ions often show an empty shell because remember they have lost the electrons from that empty shell. So they might sometimes show that it is empty. So you can see here, here's nitrogen. It's got a 3 minus charge, which means it has 3 extra electrons, right? It has the 5 that it started out with, because nitrogen has 5 valence electrons. And then it has the 3 that it gained to make itself have a stable octet, or 8, which gives it a -3 charge. Same thing here with oxygen. It starts out with 6 valence electrons. You can evenly space there. It will gain 2 more to get that nice 8 valence electrons, which give it a -2 charge. And then you see fluorine here. Fluorine starts out with 7 all on its own. 7 valence electrons. And it has the very strong tendency to gain 1 more, which gives it a -1 charge and gives it that stable octet of 8. And if you look here at the positive ions, they are empty. There are no valence electrons. But if you look at your periodic table, sodium by itself has 1. Definitely has a tendency to lose that 1, gain a positive charge. Same with calcium, has 2 valence electrons, has a strong tendency to lose them and gain that +2 charge. And aluminum, same thing, 3 valence electrons, but it will lose them and have a +3 charge because it still has 13 protons, but only 10 electrons, right? Gives it that